Thank you very much. Yeah, so as I was saying today, I'll be talking about the local and remote drivers of Southeast Australian drought, but just want to point out that the analysis framework that I'll talk about here is really applicable to other regions of the world, similarly affected by local and large-scale drivers as well. And today we'll be looking at this from a moisture transport perspective. So I just wanted to start off with the take-home message from the work, which is that during major droughts, ocean moisture did not reach Southeast Australia as often and produced less rainfall when it did. Or in other words, regional atmospheric circulation redirected important moisture away, depriving Southeast Australia of its typical moisture source. And what atmospheric moisture was available during drought was less likely to be precipitated due to a combination of land and atmospheric conditions that were generally less favourable to rainfall generation. So how did I come to that conclusion? Well, first, of course, I had to let me define what I mean by drought. Today, we'll be focusing on the northern region, which is this blue one here, which is called the Northern Murray-Darling Basin, one of the Murray-Darling Basins. You've probably heard of it, one of the largest and most important hydrological basins in Australia. And I'll be defining drought using percentiles. So as well as the rainfall climatology, we can see here on the right a schematic of what I mean by rainfall percentiles. When I speak about bottom decile rainfall, that means rainfall in the bottom 10% of the record versus top decile rainfall, which is rainfall in the top 10% of the record. So in this study, as I said, we based the drought definition on percentiles. So looking here at panel D, this is annual rainfall. So within years with bottom decile rainfall, I then look at the seasonal rainfall. So that's the bottommost panel. The first season with below average rainfall during that bottom decile rainfall year, I class as drought onset, with the remainder being drought intensification. And similarly, for drought termination, I look at a year with the top decile rainfall, and seasons within that year that have above average rainfall are classed as drought terminating seasons. So, and this is broadly similar to what you'd get with the Standardized Precipitation Index, or SPI 12. So based on this definition, within this time period, we see three major droughts occurring. The first one in 1982, then drought B, 1994, and drought C in the 2000s was the Millennium Drought. So for each of these drought stages, onset, intensification, and termination, I looked at where the moisture for rainfall was coming from, with the goal of finding out how and why it differed from normal. Now, moisture for rainfall can come from one of three places, shown by the middle picture here. For your region of interest, where there's rainfall, that rainfall or moisture for that rainfall can be sourced from the local area, so from local evapotranspiration. And if contributing to rainfall, then that's known as rainfall recycling. You can also source moisture from the land outside the region and, of course, from the ocean. So I use the Lagrangian technique to trace the path of rainfall back in time and space to determine its evaporative origin. And for each place where it rained in Southeast Australia, I traced the moisture in the atmosphere using three-dimensional winds and 2D evaporation, and accounted for moisture gain along the trajectory. So once identified where the moisture was coming from in each drought stage, I then investigated why it differed from normal. Did we have less rainfall because normal marine sources were evaporating less, for example? Or were they evaporating the same amount? They were generating the same amount of moisture, but that moisture was transported elsewhere. Or did the region receive the same amount of atmospheric moisture as normal, but conditions were not favourable to actually precipitate that moisture? I also wanted to estimate the degree to which the land surface amplified or attenuated the rainfall anomaly in each drought stage. So did it exacerbate dry conditions, for example? And if so, by how much? Can we quantify it? So again, as I mentioned, there's the three sources of moisture, three different locations that you can receive moisture from. And to estimate amplification of the rainfall anomaly by the local land surface, I simply looked at the proportion of the rainfall or the total rainfall anomaly associated with that first source of moisture, the local land. So it's quite simple. And I'll just point out here that climatologically speaking, Southeast Australia receives the majority of its moisture from the ocean, over 80%, with the remainder coming from the land. And this kind of split, or this ocean dominance, really is the same for the whole of Australia. We get most of our moisture from the ocean. So bear that in mind as we go through. So what did the analysis show? Well, firstly, we can look at how the evaporative moisture sources changed during drought. So we saw a consistent reduction in the supply of atmospheric moisture during the onset and intensification of each drought. So you can see here the orange colours are showing less moisture than normal is contributing to rainfall in the region defined by the pink polygon there. So we can see that the onset of the 1982 drought, for example, was characterised by a negative anomaly in moisture from the Tasman and Coral Seas in particular, which is the ocean to the east of Australia, which intensified as the drought went on. And we see similar things in the 94 and millennium droughts. So less moisture, we can see from this that less moisture would reach the region during drought, which is perhaps not surprising, but an interesting outcome of this analysis was to see that the Tasman and Coral Seas appeared to be an anomaly hotspot. So that led us to ask, why did the moisture supply change? So we can see here that it wasn't because those key marine source regions were evaporating less. So here I'm showing the cumulative rainfall in the first column in the red drought years compared to the corresponding drought termination years in blue. Obviously, there's lower rainfall totals during drought. But in the second column, we can see that evaporation in marine source regions doesn't really change between the drought and the drought termination periods. And yet the amount of moisture in the atmosphere above the region was lower during drought, particularly in the southern region, which I show in the rightmost column here. So in the northern region, atmospheric moisture was either lower or at similar levels during the drought and termination periods, but large-scale uplift was suppressed during drought, which is what we're showing here, what I'm showing here in the rightmost column. So large-scale uplift here I'm indicating by 500 hectopascal vertical wind speed. The average values are in grey, and we can see in the red drought years that we see a general suppression during drought. And this just suggests a lack of precipitation generating mechanisms in the region during drought, which could be a reduction in local convective activity since rainfall recycling also reduced during these periods. So the reduction in moisture supply wasn't due to reduced evaporation in the key source regions. So the same amount of moisture was generated, but it was transported somewhere else. And this is what we can see by looking at the anomalies of the low-level wind speed during the drought onset and intensification stages. We see anomalies in the regional circulation moving away from the region, as we can see here, most clearly during the drought intensification stages. Interestingly, this situation reversed during drought termination. So in all three cases, there was anomalously strong easterlies advecting moist marine air from the Tasman and Coral Seas into the region, which could then contribute to rainfall. Now, I've been focusing on the ocean a bit so far, but of course the land played a role. So we can see here that less moisture than normal was contributing to rainfall during drought from the land, which is perhaps not surprising given that the land surface was drying out. But I wanted to know how much did the land surface exacerbate the low rainfall situation. So if we go back to our measure of land surface amplification, we can see that the terrestrial anomaly accounts for up to 6% of the rainfall anomaly across the drought stages, which is actually more than normal, more than the non-drought period. From this table, you can see that the local terrestrial amplification is lower than the non-local, so the dark green around here, and also from the ocean. And as I pointed out before, the ocean is really the dominant moisture supplier for rainfall in Southeast Australia, so it's going to have a larger role in amplifying any rainfall anomaly. And that's why I say that the role of the land surface could actually be more than 6%, and probably is, once you start looking beyond pure moisture counting and consider the impact of surface heating and surface fluxes on the evolution of the boundary layer and eventual precipitation of available moisture. So to sum up what we've learnt from this analysis, we can see that droughts have distinct signatures in terms of moisture that either reaches or doesn't reach the region. And this appears to, at least for Southeast Australia, be mainly due to circulation anomalies redirecting marine moisture, in particular from the Tasman and Coral Seas to the east of the continent. And this suggests that we need to investigate the impact of synoptic systems and large-scale modes of circulation on the relationship between zonal winds, moist advection, and rainfall in drought-prone regions of the world like Southeast Australia. The results also suggest that drought in this region wasn't solely due to a lack of atmospheric moisture, but also due to a lack of mechanisms able to precipitate what moisture was actually there. So we also need to investigate the mechanisms responsible for the suppression of rainfall during drought. And finally, we need to investigate whether climate models are able to simulate these drought signatures, and why or why not. And this was just a summary of work that has been published, as you can see here, if you would like more detail. And with that, I'll stop and say thank you.